All right, today's topic is going to be a slow transition from descriptive statistics towards inferential statistics. So remember, a couple of days ago we have discussed that statistics as a discipline consists of two unequal parts, right? There is a smaller part called descriptive statistics, and it's relatively straightforward and simple. So, for example, take a data set and make a picture of this data. Make a bar chart or a histogram or a pie chart. So show how the data is distributed. And then also characterize the data set with a handful of numerical characteristics, right? Such as, for example, central location. We learned that there are three main ones: mode, median, and the mean. Variability can be characterized by range, but that's not very straight. It's very straightforward to compute, but not very useful measure, right? Then there is variance. Closely related to the variance, there is a standard deviation, and there is interquartile range, coefficient of variability. So these are the measures that are primarily used to characterize the variability. And then also there are measures of measures of relative standing. Percentiles, right, and specifically quartiles. But you can, of course, calculate custom percentiles as well. So all these things, they're used to somehow characterize the distribution or population or sample, what have you, any data set that you have. So that was in the land of the descriptive statistics. But the majority of this class is going to be dedicated to inferential. And we have to discuss first sampling distribution. What is it? All right, sampling distribution, well, the name pretty much says it. It's the distribution that is related somehow to samples, to sampling. So let's actually take a look at the problem. This problem comes straight from the textbook that you may or may not have, because textbook is optional, right? So, manufacture of cans, cat food. How many of you have cats? Okay,
My wife has a cat. I don't have a cat.
Yeah, but you have a cat too, right? Your wife has a cat, that means you have a cat.
Yeah.
Yeah, same here. I have a cat. Sweet creature. So, and of course, all cats, they like cat food, right? Whether they're hungry or not, they're always hungry, right? They're always asking for food. So, manufacture of the cat food. So they produce these cans, right? Tin cans. Filled with chunks of processed meat and gravy and all that stuff. First of all, let me ask you this question. How do you think these cans are being manufactured? Are they manufactured in big quantities using automation, or are there a lot of people that, using like some sort of the, spoons or scoops, they place this food into the cans and they seal them manually? It's automated, right? Because it has to be manufactured in large quantities, in millions on a daily basis, right? So therefore there is equipment that essentially, pretty much conveyor belt. So the cans, empty cans, move down the conveyor belt, and then there is probably like a valve that's connected to the reservoir filled with food, right? The valve opens up, can is being filled, and then valve shuts off when it measures pretty much enough of the food, right? So let's say that these cans are supposed to contain 6 ounces, each one of them. Well, let me ask you this question, true or false? Every single can, if you open it up and measure what's inside, it will contain exactly, precisely, no more and no less than 6 ounces of cat food.
False.
False, right? Why? Why false? Because there are many factors that come into the play, right? For example, it can be that the food is chunky, it contains chunks, right? So one extra chunk drops, right? It gives a little bit more weight than 6 ounces, or other way around. It shuts off, before this chunk falls, and therefore it's slightly underweight, right? Then there is such thing as how precise are we shutting off the valve? Millisecond earlier or millisecond later can make a difference, whether or not this extra chunk falls in, right? And then the valve can become clogged over time, right, as it dispenses more and more cat food. Basically, the clog can build up, and therefore you can see like you put less and less food in every can. So there are a lot of factors that can affect what happens with every single can. All right, and let's say that you talk to the production operations manager of this plant, and this guy tells you, well, on the outside of the can it says 6 ounces, but in actuality our equipment is set up to put on average higher than that. Okay, average net weight is 6.05. So they're kind of giving away a little bit extra for every can, right? So and there is a standard deviation of 0.18 ounces, and the weights are normally distributed. So in other words, here's what he's telling you. Let me bring up the my drawing tool. So here's what he's telling you. If you consider all possible cans that they manufacture, the distribution of weights looks like that. It's a normally distributed process. Okay? Because of factors that we have discussed, right? Millisecond later or millisecond earlier shut off of the valve makes a difference. Whether or not extra chunk falls in makes a difference. The buildup of material makes a difference. So cans basically are not the same. In fact, you will very rarely find exactly two similar cans, right? So he's telling you that the average that they have, the mean, is 6.05 ounces, and the standard deviation is 0.18. So why do you think they, from the standpoint of this production manager, why do you think they set their equipment to fill up cans with 6.05 instead of 6? What do you think is the...
Is the size of standard deviation?
Well, yeah, here's the idea. What if they set up the equipment at precisely 6.0, like it's supposed to say on the outside of the can? That means that half of the cans will be overfilled. As a customer, do you have a problem with getting a little bit more product for your money? No. But half of the cans will be underfilled, right? Does that represent a problem? Yes. And half of the people will get their cans noticeably sometimes underfilled. So therefore, the manager of this plant, production operations manager, they make a conscious decision to go ahead and kind of give away on average some extra weight for every can, right? Why is that happening? Well, because if you're looking on the label where it says 6 ounces, this is where your 6.0 is located, okay? So in this case, you will still have underfilled cans, right? No matter what you do, you will still have occasionally underfilled cans. It's the question of what is percentage of the cans that are underfilled. And in my case here, all underfilled cans are going to be in the left tail, and that now is going to be less than half, right? Less than 50%. So whatever this area is, I don't know. We can compute that certainly, right? Say, for example, it's 0.3. So only 30% of cans are going to be underfilled. And that's better, right? So that's pretty much a conscious trade-off that these people running the plant are making, okay? But this is the situation that he tells you how it is. 6.05 is their average, or they believe that 6.05 is their average. And the standard deviation, historically, they collected some data earlier, right? And they analyzed the data, and it turns out that 0.18 of an ounce is their standard deviation. Okay. So what you do as a observer, sort of outside observer, you're saying, okay, well, it may or may not be the case that your average is really 6.05. I don't know. Let me measure some things. And what you do is you take 4 cans randomly out of their production line, and you calculate the average. So, of course, every can will weigh differently, slightly differently, right? So, therefore, you're going to get, let's go back. You're going to get, let's say, can number 1 is right here, okay? Can number 2 is right here. Can number 3 is right here, and here's your can number 4. So when you compute your average among the 4 cans, your average turns out to be X bar, 5.97 ounces, okay? So after that, you're saying, okay, well, I didn't expect it to be exactly 6.05. There's probably going to be slight variability anyway. But is 5.97 close enough to 6.05, or is it not close enough? Okay? If it's far away, what you're going to say? If it's very far away from 6.05, you're going to say, well, my sample doesn't look like it confirms your statement that on average, your average weight in the can is 6.05, right? But if you find out that 5.97 is close enough to 6.05, you're going to say, well, yeah, probably you're right. Probably you're right. At least I don't have the proof to tell that you're mistaken, right? Or you're lying. It's close enough. Of course, there is some variability, but these two numbers are close enough. So probably what you're saying is really the case. Okay? So how do we make this judgment? Is 5.97 close to the claimed average 6.05, or is it far away? Well, let's discuss sampling distribution. What's a sampling distribution? And this slide took me quite some time to put together. All right? Sampling distribution, first of all, we have two different types of data. Well, three different types of data, but if you look from the bird kind of view standpoint, there are two of them, right? There is a numerical or continuous data, and there is categorical. Nominal, ordinal, they're both categorical data, right? And sampling distribution actually applies to both of them. So let's first take a look at the numerical data. All these points on the top, right there, are my individual cans. So this is my population. Okay, so if I open up every single can and measure precisely the weight in this can, I will open millions and millions and millions of cans. That forms a population distribution for me. Okay, but of course I'm not going to do that, right? So, but let's say let's perform kind of a mental experiment. Let's suppose that we're going to randomly pick samples of 4. So the conveyor belt moves, right? And I pick up 4 cans, I open them up, measure precisely every one of them, compute the average. Okay, that's going to be my sample 1 average. And then sometime later, I do the same thing. Pick up 4 cans that I randomly select, open them up, measure the content, compute the average. It's going to be a different average, right? Because of variability. Then sometime later I do it again and again and again. So I keep picking samples of 4, and for each sample I compute average, compute average, compute average, and compute average. All averages are going to be different, so therefore they by themselves will form their own distribution. So distribution of all sample averages. And that is called sampling distribution. So let's see how the animation works, and if it does actually work on this slide. All right, so here's what I do. I pick up 4 cans. That's my first 4 cans. They're all different. And then average is going to be in the middle, right? We discussed that average is kind of the center of gravity for your data set. So here is my average. Points, individual cans, I move up to form the distribution of my population. And the single average for my sample, I move down so that I accumulate more and more sample averages, and they start forming their own distribution, sampling distribution. So individual cans go up for the population distribution, sample averages go down. Another sample, 4 cans. All measurements are different, therefore the average is different. The average I put down as a part of my sampling distribution. The 4 points I put up as a part of my population distribution. And I keep doing that again and again. 4 cans that are pretty close to each other, right? And the next sample, I have far apart, but my average is going to be kind of in the middle. And then here is pretty compact group, all right? So I keep doing that again and again and again, all day long. 4 cans, average, 4 cans, and their average. All right, another 4 cans. So what happens? So I started actually getting 2 different distributions, right? 2 different distributions start to form. On the top I have my population, every single can measured individually. At the bottom I have my sample means, how they are distributed. So if I would ask you about the center of both distributions, like just kind of eyeballing the picture that you have up there, what do you think? Center of my distribution, of the population distribution is right here, correct? It's right here. All right, and the center of my sampling distribution is approximately in the same area, right? I don't have enough points. So statisticians basically showed that there is an exact match. The means for your distributions, for your population distribution, and for your sampling distribution are exactly the same. What about the variability? Which one is more variable? The distribution which is up top or at the bottom? Variability is the measure of inconsistency, right? Which one is more consistent? On the top or at the bottom? Bottom one is more consistent, right? Because there is less spread of points, right? In general. So therefore, what happens is, as we move from population distribution to the sampling distribution, the means do not change, they stay the same, essentially, right? But the variability gets smaller, right? Points are more consistent, distribution is less wide. So means are the same, these two lines illustrate that, but variability is lower for the sampling distribution, okay? So here is approximately the range for my population distribution, and the range for the sampling distribution is much smaller, okay? All right, so we're going to use these two facts later. So if you take a lot of samples, we took only, 10 maybe samples, not more than that. But if you keep taking a lot of samples, on the top you will have the distribution of the population forming. And we know from the settings of this problem that it's normal, right? With average 6.05 and sigma 0.18. And at the bottom you will also start looking at the shape that looks a lot like normal distribution. In fact, in a second we're going to discuss that. All right, so here are two rules that apply always, regardless of what kind of population you have. Your population of cans can be distributed normally, or it can be right skewed, or it can be left skewed, or it can be bimodal or trimodal. Whatever the shape and form of your population distribution, these rules apply always. They're universal rules, okay? The first rule says that when you are creating the sampling distribution, your averages are going to be the same. Okay, so right here it says that the average for the population, mu, is exactly equal to the average of the sampling distribution, mu for all x bars. So means coincide always, regardless of what population distribution looks like. Okay. The second rule basically says that your variance, or measure of variability, for the population, for the sampling distribution, is going to be smaller by the factor of n than the variance of your population. Okay, and that's what we saw on the previous couple of slides, right? Variance is smaller. That means that the population, the distribution is more compact. Okay, so as you start creating your sampling distribution from your population distribution, it's going to look more concentrated around the mean, right? And that reflects the fact that variance is getting smaller, and therefore standard deviation is getting smaller, right? Because standard deviation is linked with variance, okay? So the formula right here says that standard deviation for the population distribution is smaller by the factor of square root of n, where n is what? N is your sample size, right? How many items you have per sample, okay? So these are universal rules that apply always. And these slides, by the way, are posted, okay? I believe I updated the slides yesterday out there. Okay. So central limit theorem, it's the fundamental result of statistics, okay? So half of the tests that we're going to learn in this semester, they will be pretty much based on central limit theorem, right? What does it say, central limit theorem? It says that if you know, well, first of all, let me point out that these rules are universal, right? They apply regardless of what your population looks like. Is it normal? Is it skewed right, left, or is it bimodal, trimodal? Doesn't matter. Means are always the same. Sigmas are always related like that.
So you say the population mean and the average. The population mean will always be equal to the sample mean?
Yep. Population.
You take enough samples.
No, not the sample mean, but sampling distribution mean.
Okay.
Yeah. So every sample that I take will have a different average, right? So it will jump all over the place. But the distribution of all x bars will have its own mean, right? So mean for all x bars, so mean of all the means, so to speak. It kind of sounds weird, right? But that's what it is essentially. We have distribution of sample averages, sampling distribution. All right. So first result of the central limit theorem, very fundamental, says that if your population is normally distributed, it's bell-shaped, then your sampling distribution is also going to be normally distributed, regardless how large or small your sample is. You can have a sample of 2, very small sample, not even statistics, right? Just 2 items. Your sampling distribution is normal. If you have sample size 5, or 17, or 28, or 150, doesn't really matter because your sampling distribution will always be exactly, precisely normal. Now, to be honest with you, there are not a lot of things that are normally distributed in the real life. Most of numbers are distributed with some sort of the skew, and we've seen examples of the skew distributions. Salaries in the society are distributed severely right skewed, right? So there is a sharp peak at the beginning, and then there is long tail on the right. Insurance claims are right skewed. Amount of money that you spend on the car, fixing your car, depending on the mileage, it's left skewed, right? So typically the distribution of things that you're seeing in the real life, they're skewed, or they're not normal. Okay, so then what happens? You still can get samples, right? And you still can get sample averages and collect them together, plot the distribution. You're going to get sampling distribution. So the second fundamental result of central limit theorem says that if your population is not normal, that is still okay. If you take sufficiently large sample size, then your sampling distribution is going to be approximately normal, so almost normal. Okay, and the larger your sample size is, the more normal your sampling distribution is going to look. Okay, now note that here on the slide it says if you have a sufficiently large sample size n. Well, what is sufficiently large? How large should that be?
10
10? How is it?
times n.
10 times n? Well, we're talking what the n should be. Yeah, sample size. What should be the sample size for us to stop worrying about the population distribution and say, hey, that's large enough, therefore my sampling is going to be normal no matter what? The actual answer is, well, if you look at different textbooks, you will see different answers. So that's basically a blurry area. It's not exact science, okay? So some textbooks will tell you 25, okay? The textbook that I referenced, 30. So if you have sample size of 30 or more, then you can pretty much assume that your sampling distribution is normally distributed, okay? All right, and you know what? Just to give you kind of an intuitive insight into why that might be, why in the limit of large sample sizes we're starting to get more normal and normal looking distribution. Here is the kind of example that I came up with so that I can illustrate why is that happening. Hold on, I'm gonna have to go back and reset the screen resolution because I showed you the animation, right? It created, created the whole split effect. Okay. So this is an intuitive explanation. What I'm going to show you is kind of intuitive explanation why things tend to become more and more normal as you start taking samples. Okay. Well, let's say, for example, I have, let me create a new page here. Let's say that I have severely non-normal distribution of the population, like this. For example, okay, I have one peak over here and then another peak over here. Does that look like a normal distribution? No, highly abnormal, right? And let's say that these two peaks, the left side of the distribution and the right side distribution, they're exactly the same, so it's a symmetric distribution, okay? And let me be simplistic. I'm going to set my sample size to only 2, okay? So let's say, let me consider what are the possibilities. I take two items from my distribution, right? Where they can come from? Well, one possibility is that my, so let me call this a left side of the distribution, this is the right side of the distribution, okay? So I take two items. One possibility is that both of my observations that came from the left side of the distribution, left. Okay? And another possibility is that the first comes from left side and another comes from the right side, correct? And yet another possibility is right left, and yet the last possibility is right. Okay? Make sense? Okay, so what happens if both of my observations came from the left side of the distribution? I have point right here and I have point right here. And let me kind of, at the bottom, I'm going to draw the specific sample averages. Okay? So I have 2 points from the left side of the distribution where the average is going to be located. Somewhere between them, right? Kind of in the middle. So the middle is the point right here. So this is my first x bar. Okay? So this point right here is my x1 bar. First sample average, right? Second possibility. Observation number 1 comes from left side of the distribution, and observation number 2 comes from the right side of the distribution. Like that. Again, I compute the sample average, and it's a point in between, right, in the middle. So it's right here. So I put it down. This is my x2 bar, right? Option number 3, from right side and from the left side. So one point comes from here, another point comes from here, and the average is in the middle, right here, and I put it down, x3 bar. And the final possibility is right. So one point comes from right, another point comes from right. Here is the average, and I put it down there, and that becomes my x bar number 4. Okay? So what do I see? I see that out of my sample averages, 1 point is on kind of extreme left, 1 point on my extreme right, but 2 points out of 4 were in the middle. Okay? So what I'm getting is points start to concentrate around the center, okay, where I didn't even have anything at all, right? In the middle of the distribution, where I had the valley, that's where my sample averages start to concentrate, okay? And the more points I take, the more it's going to look like that, right? And moreover, if I start to increase the sample size, so instead of 2, I'm going to take, for example, well, let's say 50, okay? Now my sample size is 50. Points are going to come from all over the place, right? But the majority of my samples are going to contain kind of the balance, 25 points from the left side, 25 points from the right side. Sometimes they're going to be slightly imbalanced, right? I'm going to have 24 from the left, 26 from the right. Sometimes more imbalanced. For example, 20 versus 30, right? Occasionally, rarely, I'm going to have highly imbalanced, like 15 versus 35, okay? Or 10 versus 40. But the majority of the points will be evenly distributed between the right side and the left side. So the majority of my samples are going to end up in the middle. Okay, that's where my averages are going to be. So therefore, if I'm going to start kind of shaping the distribution, it's going to start looking more and more and more normal. That's kind of an intuition that I came up with over the years. Okay, it's not scientific at all, right? It's not approved by any stretch of imagination. Okay.
It makes sense.
Yeah, but it's kind of an illustrative example, okay? So that it kind of tells you, what might be happening, why most points tend to concentrate in the middle. And that's what makes the normal distribution so special, right? You start taking samples, you start averaging them out, you start plotting the averages. The majority of the averages are going to concentrate in the center, and then if you go to the right and to the left, you will see less and less and less points that are extreme. So things are going to start looking more and more and more normal, right? Okay, so now let's take a look at our specific example. Okay, so let's go back to the example with cat food. So the foreman or operations manager tells me that they put 5.05. That's their average. That's what he believes the average is. Okay, when I'm getting my my sample of only 4. I see 5.97. Is that too far away? And therefore I can say, well, it's just not consistent with what you're saying, just too far away. So probably either you get your numbers wrong or your equipment is out of tune or something is happening, okay? Or is it close enough? How do I judge that? Well, let me go ahead and apply the central limit theorem, right? So what do I know about the distribution of my, of my cans? right there. Okay, it says that the weights are normally distributed, and I believe that the mean is 6.05, and the standard deviation is 0.18. All right, let me go back to my drawing. I believe actually I have, yeah, I have it here. All right. So here is what's happening, right? I have this distribution. This is his claim that the mean is equal to 6.05, and this is what I find out, right? That's ugly. When I take my sample, it turns out to be kind of a little bit on the low side, 5.97. So how likely is that I randomly pick 4 cans and I get 5.97? Is it close or is it not close? Well, first of all, if I keep taking my cans again and again and again and again, cans of 4, right, and plot all the possible sample averages, I'm not going to do that. I have only one sample. But if I did, I would get sampling distribution, right? So we know that my weights, let's call them W. That's my random variable. Weight of the can, W, right? So Foreman tells me that the weights are normally distributed with the mean 605, that's what I set up, and standard deviation sigma 0.18. I selected the sample size of 4, right? What do we know from the central limit theorem? From the central limit theorem, we know that if your population is normally distributed, then your average weight of cans in your samples are going to be also normally distributed, right? So therefore, that much I know. W bars, average weight in each sample, if I plot their distribution, I'm going to get a normal distribution. Sampling is normal, okay? What else my central limit theorem tells me? That the average for the sampling distribution is going to be same as the population, 6.05, right? How about the standard deviation for all X bars? It's going to be higher or smaller? Yeah, it's going to be smaller, right? Smaller, by the factor of square root from the sample size, okay? So therefore I have to take 0.18 and divide that by the square root from, oops, can't write, square root from 4, that's my sample size. Square root from 4 is 2, right? 0.18 divided by 2 gives me 0.09, right? So therefore, what I'm going to get from, let me erase some of that stuff and just write it out. Mu x bar 6.05 and sigma for x bars 0.09, right? So my sampling distribution is going to have the same exact average, right? So I'm going to draw the sampling distribution at the bottom. Same exact mean, mu for x bars is going to be x bars precisely 6.05, same thing, all right? But is it going to be more spread to the right and to the left or less spread if sigma is lower? Going to be more concentrated or less concentrated? What do you guys think? Christian, what do you think? Sigma is getting lower. So it's going to be more concentrated, right? Yes. It's going to be less variable. Yep. Exactly. More concentrated. So same peak, right? But there is less of a spread that's going on. Okay. So this is how my W average W bars are going to be distributed. All sample averages, right? So that's my sampling distribution. And I'm just getting one sample, right? Just 4 cans. That's it. And the weight turns out to be right here. And that's my X bar. X bar equals to 5.97. Okay. So here's what I can compute. I can compute how likely was that to see that type of sample average, 5.97, if the Foreman is actually right. If that number, 6.05, is the actual population average. So he was not misled or misinformed, or, you know, this is the actual thing, what's happening. How likely is that for me to observe that sample? And that's going to be the area in the left tail of my distribution, okay? Now, of course, I cannot ask the question, how likely is that for, I mean, I can, what is the probability to get exactly that sample, 5.97? 0, right? We discussed that. For continuous distributions, probability of a certain fixed given number is always 0, right? So therefore, that does make sense to ask that question. But I can ask a question about how likely is that the sample is that extreme, 5.97, or even more extreme than that. So anything in the left tail of the distribution, that's going to be samples as far away from my mean 6.05 as 5.97, or even further away, right? And that I can compute, of course. I need to use some sort of the software for that. Well, that would be JUMP in our example, in our case. But let's go ahead and do that, actually. Make sense? All of that? Okay. Let's go back, and this time I believe it's going to work for us. Yes. So let's switch to JUMP. All right. And we're going to use the same exact tool as we did before for distribution considerations, right? So from help, sample data, and here we need to look at teaching scripts, interactive teaching modules, and distribution calculator right there. Okay, so here is my distribution calculator, and I need normal distribution. My mean is going to be the same as for the population. That's what the foreman says, 6.05, right? 6.05. But my standard deviation of the sampling distribution is what? 0.09. We computed that, correct? And this is how all the sample averages are distributed. If I was sitting all day long taking sample, measuring, that's how the distribution is going to look like, right? For all sample averages. My sample average specific is, well, first of all, I'm looking in the left tail. So x less than q, that's the right thing to do, right? And I'm looking for 5.97 or smaller. And here is my area, shaded area, and numerically is 0.187. So now we have to ask ourselves, right? Is that large probability or is that small probability? Realize that what I just computed, this number 0.187, is the likelihood if the foreman is actually right. And I'm believing him, right? It's like innocent until proven guilty kind of deal, right? Almost hypothesis testing, actually. If he is right, and I don't have reasons to suspect otherwise, and 6.05 is our true average, that number tells me how likely is that I purely randomly pick 4 cans, and it happens to be sampled with average 5.97 ounces, or even smaller than that. So almost 20%, or 19, 0.187, 0.187. So now we have to ask ourselves, is that a big probability or is it a small probability? Therefore, we need to have a measure of what's small and what's large, right? And this measure, actually, in statistics, is called significance level, right? So significance level, one way to think about that from the business standpoint, it's a yardstick between what is a small probability and what's a large probability. Anything smaller than significance level alpha is considered to be small probability. Anything larger than significance level alpha is considered to be large probability. Remember we discussed that on the very first day. What is the standard value of the significance? 5%, 0.05. So if we kind of adopt that mindset here in this in this exercise, then what do we say? 0.187 is higher than 0.05, right? So therefore, that probability is large, right? So what do I conclude? I'm going to say that likelihood, if the foreman is right, and 6.05 is the actual average that they're running in their production line, and likelihood to see the sample that I've seen with 5.97 or even smaller than that is 18.7%. That's the likelihood to see what I'm observing, right? And that's not small probability according to my scheme of things in life, right? I believe that 0.05 is the yardstick. So that's a large probability. So therefore, what I'm seeing actually is consistent with what he's saying, right? Kind of imagine that my probability would be small. So suppose that this computation would yield me not 0.187, but something like 0.02, only 2% chance. And what would I say? I would say that if you're right about your average 6.05, and what I'm seeing happens in only 2% of the cases, purely randomly. Okay? So I can go kind of two ways from here. Okay? I can say, well, I'm witnessing a miracle right now. Very rare event, only 5%. Very unlikely event, low probability event. Okay? And that can happen, of course, right? Or alternatively, I can say, well, let's say that really typically there are no miracles. Okay? We don't see them a lot of miracles. So therefore, it's not a miracle, it's just the fact that your estimation of 6.05 as your mean is too optimistic. Okay? You have outdated, data or something like that. So it's not 6.05 likely, it's smaller than that. Okay? So that kind of gives you a glimpse into the future of what we're going to be doing tomorrow or Monday, hypothesis testing. That's very close to what hypothesis testing entails. Okay? All right. So let's...
So in this,
Uh-huh.
go back to that real quick.
Okay.
So in this particular example, why wouldn't we put 0.18 as the standard deviation given the problem?
Why would we put...
We calculated 0.09. Why wouldn't we put 0.18 in there? Is that what's the given problem?
Why this standard deviation is not the original one, right?
Right.
Oh, okay. Because really, I'm talking about the sample right now.
Sample,
Right?
okay.
Yeah.
There
So
was
therefore,
population.
yeah.
Okay.
0.18 was population standard
Right.
deviation, but I took a sample, so it should come from sampling distribution, right?
Exactly.
And sampling distribution has this smaller standard deviation. Okay. All right. So actually, you know what? I believe I can even provide you with pretty cool demonstration. So after that, we're going to do this example. But as it turns out, JUMP has a pretty cool demonstration of sampling distribution. So let's spend 5 minutes just looking at it. Okay. So if I go to the same exact place, all right, I need to go to help, and then sample data, and teaching scripts, same as calculator for distributions, interactive teaching modules. I have two sampling distributions, one for sample means, that's pretty much what we discussed, another for sample proportions. We didn't discuss that yet, but we will at some point. Okay? So sample means, sampling distribution of sample means. All right, so let's take a look. I'm going to make it bigger, both of them. So up here at the top, I have distribution of sample data, and so in other words, every sample that I'm going to take from my population, over here I'm going to have a histogram of that sample, how the sample looks like. Okay, and at the bottom, every sample will yield 1 point, sample average, and all sample averages will be accumulated here to form a distribution of all sample means, or as we know it, sampling distribution. Right? So my population, I have several choices. It can be normal, it can be skewed on the right, or it can be uniform. So let's take a look at actually these two, normal and skewed to the right. So let's start with normal. What do we know from central limit theorem? If my population is normal, sampling is normal, always, right? Regardless of small sample size, large sample size, huge sample size, doesn't matter. Sampling distribution is always going to be normal, if the population is normal. All right, let's actually go ahead and do our previous, well, let's do exactly this, what we just did, right? 6 point, yeah, Kent, right? So my population mean is going to be what? 6.05, that's what my foreman told me, right? And population standard deviation is going to be 0.18, yep, 0.18. All right, and I'm going to call this variable not height, but weight, right? That's what we decided to do, weight of the can. Well, let's start with small sample size. Let's say I'm going to have 5 only, well, no, actually, let's do exactly what the problem says. 4 cans per sample, right? What the slides say, let's replicate it in the software. And let's do 100 samples. We have two options here. Animate, in other words, see things in dynamic over time as we collect sample, 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 or just click and get it. You want to see the animation? No? All right, let's see the animation just for the heck of it, right? And I'm going to say draw additional samples. And up top, what it starts to do is I have right now 58 samples, 75, etc. So every sample, it shows how the sample is distributed. That was my last one, number 100, right? That's pretty good sample, right? PDN, pretty darn normal sample. Not all of them are normal, right? You've seen all kinds of weird stuff, right? All over the place. Okay, but what do you see at the bottom? At the bottom, every sample generated a point, right? 1 point. And that point became part of this distribution, histogram. So, does it look like it's more or less symmetric? Yeah. Give or take, here or there, right? Some area. Does it look like it's bell-shaped, more or less? Normally distributed? More or less, yeah. So let's draw additional 100 samples, right? Let's actually do 500 samples, right? So let's run this thing for another 400 observations. That probably should give us enough of the, of the shape, right? Enough details. So I just click draw additional samples, and it starts taking samples more and more, and they add, of course, to my sampling distribution, right? I'm going to leave it alone so that it can work without interruptions. So you can see that on the bottom, the picture starts to shape more and more like normal distribution. I still have some imbalances. Yours probably, if you're running that right now, yours looking different, right? Because of randomness, right? My random numbers are not the same as your random numbers, obviously. Okay, but I'm pretty much more than halfway through, and it starts to shape PDN, pretty darn normal. All right. And that's just sample size of 4, right? That's not a huge sample size. So it's going to run for another approximately 100 samples. And I still have this peak right here. Almost there. And there it is. There is your 400 extra for a total of 500 samples. So it looks a little bit asymmetric in my case, right? But overall, it's a bell-shaped distribution, okay? For the sample size of only 4. What happens? Let's see what happens if I change my sample size to, let's say, let's go with 30, right? Because 30, remember, it was a magical number, right? Sample size of 30 gives you pretty much the exact normal distribution regardless of your population is, right? Normal or non-normal. So what do you think will happen if I go with 30 and I'll go with 500 samples, but I will not animate that, okay? So no animation. What do you think will happen? It's going to look normal, right? What about how wide the distribution is going to be? Do you expect it to be wide or fairly sharp and concentrated? Fairly sharp, right? Because remember, sigma is getting divided by the square root from the sample size, right? Sample size is getting larger, standard deviation is getting smaller, so distribution is going to be more concentrated, right? So if I just go ahead and draw 500 samples without animation, there it is, okay? So distribution indeed is more compact, right? And not as much spread as my previous one. But that's normal population. Let's go ahead and switch to the skewed population, skewed to the right, okay? So that means that my shape is going to have, shape of my population distribution is going to have a bulk of the data right up front and then long tail extending to the right. And probably as I draw more and more samples, let's animate this time around, okay? And let's again start with four samples, or 4 items per sample, okay? So as I see more and more samples, you will probably see in the distribution of samples that all of them are going to be skewed more or less to the right. So samples will follow pretty much the distribution of the population where they come from, right? So draw additional samples, and there you go. And you can see that this one, for example, it's right skewed, right? And most of them are right skewed. So there is a peak, and then there is a tail going to the right. And my sampling distribution starts to form at the bottom. What do you know about the sampling distribution? It is skewed to the right, okay? Why do you think that happens? Because my sample size is just not high enough, right? It's only 4. So it pretty much repeats the shape of my population, right? At that sample size, it doesn't make much difference. It's more concentrated, it has less variability, less of a sigma, but the general shape stays there in place, okay? So I'm halfway there, and then we're going to run the same thing, same 500 samples, but with a higher sample size, like 15, for example, right? And then we're going to get to 30 and see what happens, right? At 30, my sampling distribution should look pretty normal, right? It doesn't look normal right now, and it's visible, right? It's visibly skewed to the right. We're almost there at 500 samples. And this is clearly not a normal distribution, right? Sampling. Okay. And now, let me go ahead and, here it is 500 samples. Let me go ahead and change the sample size to, let's say 15. I'm going to turn off the animation, and let's see what happens. So I draw additional samples, and there it is. So what do you think about the distribution at the bottom, sampling distribution? Is it looking more normal? More normal, right? Almost perfect. So what happens if I have 30, and I reset this thing, and draw additional samples? Same thing, right? But it's more concentrated right now, okay? It's less spread. And that's the effect of sample size. Sigma is getting smaller by the factor of square root from n, right? The sample size is getting larger, distribution is getting more concentrated and less spread to the right and to the left. Make sense? What do you think? Is it a good tool to illustrate sampling distribution? Yeah. All right. Let's take a look at this problem. Actually, we probably have enough time to do this problem in a couple of ways, okay? At least one part of this problem in a couple of ways. Foreman of the bottling plant. Bottling plants, what do they do at the bottling plants? They fill up bottles with Coke, right? So the Coke or Pepsi that you buy actually was not produced by the Coke. Coke produces only what? The secret ingredient of the secret ingredient soup, right? So this, it's highly guarded, right? Coke has the recipe of their syrup. I believe it's somewhere in the bank, right?
Yeah, yeah, it is. Only 7 or 8 people know the formula.
Yeah.
My friend, real quick, my friend's father inherited from his great-grandfather 17 shares of Coca-Cola stock. Dated back in 1970, 17 shares. And today, when he cashed them out 10 years ago, like 15 years ago, they were about $10, $15 million.
Oh, wow. That is a lot. Yep. So Coca-Cola Incorporated, really, they produce only the syrup, right? The secret ingredient. And then they distribute this syrup to bottling plants. And bottling plants take care of the rest. Okay, they take the carbonated water, mix with the syrup, and fill the bottles. Now, I'm sure all of you were in grocery stores, right? And you've seen aisles filled with these bottles, right? If you next time when you walk in the aisle, just note the level of the liquid, right? Is it the same at every bottle, or as you look across the aisle, it kind of like goes up and down? That's what happens, right? Up and down. So that means that there is variability, right? There is always variability. It's just inherent to anything that we do, okay? We can't create exactly 2 similar cans of cat food. We can't fill up every bottle with exactly the same amount of Coke or Pepsi, okay? There is always variability. We can try to minimize it, to improve the process, to buy better, more precise equipment, etc., okay? But variability is always there. So, foreman of the bottling plant observed that what they put in 32-ounce bottle, actually, it's a normally distributed thing, right? The amount of soda that we put in every bottle. But the average that he calculated was 32.2 ounces and a standard deviation of 0.3. So what we have here is, let me create a new page. What the foreman is telling us, the amount of soda, let's use a different letter for our random variable, right? The amount of soda that we put in each can is normally distributed with the mean of 32.2 ounces and the standard deviation sigma equals to, how much was that? 0.3 ounce. All right, standard deviation of 0.3 ounce. So the first question asks me, if a customer, anybody, Christian, comes today to the store and picks up a 32-ounce bottle, what is the likelihood that he will buy a lucky bottle that will contain more than what's advertised on the label, more than 32 ounces. So here we're talking about just one observation from the population, right? So what I have graphically here in this problem is this. This is my distribution of the S, okay? The entire population, the amount of soda that I put in every bottle. It's normally distributed, and it looks like that. Okay? The average, according to the foreman mean, is 32.2 ounces, and the standard deviation is 0.3. And Christian comes to the store and he buys the bottle, and the bottle likely contains more than what they advertised. And what they advertised is right here somewhere, okay? So this is 32.0. So what Christian is seeing in his bottle is this, right? More than 32 ounces. And that represents everything in the right tail of my distribution, right? So I can easily compute that using my distribution calculator. So let's go back to jump, just like that. And I'm going to X out of sampling distribution and go back to distribution calculator. So Foreman says that everything is normal, and 32.2 is our average, and 0.3 is our standard deviation, and we're looking for the values to the right from 32.0. Kaboom. All right, so likelihood of that happening for Christian is 74.75%. He has a pretty good chance to get more than what he paid for, right? Paid for 32 ounces, get something extra. All right, 74.75. So probability that in a single selected bottle the amount of soda exceeds 32.0 ounces is 0.7475. Okay, good. Now the next question is, if Christian at the same time buys not just a single bottle but a carton of 4 bottles, okay? What is the likelihood that on average in this carton of 4 he will get more than 32 ounces? It's not just one bottle, it's the average of 4 that he bought, okay? Some bottles can be underfilled, some bottles can be overfilled, it's all over the place, right? But what's the likelihood that on average this pack that he bought, a 4-pack, is overfilled, right? More than 32 on average. Okay, so it looks like what Christian is doing is he's saying, well, this is a population, right? And out of population, I'm taking a sample of how many? 4, right? Okay, so let's see how the population, how the sample averages are going to be distributed. Well, rule number 1, ladies and gentlemen, if my population is normal, my sampling is normal. So therefore, the average amount of soda in the 4-pack is going to be distributed normally. What about the mean for these X bars? Rule number 2 says the means are always the same, right? Means are always the same, 32.2. Okay, and how about the standard deviation, sigma, for X bars? Sigma is actually getting smaller, right, by the square root from n. So therefore I have 0.3 divided by the square root from 4, because n is 4. Square root from 4 is 2. So therefore I'm getting standard deviation for the sampling distribution 0.15. Okay? So if I'm reading this correctly, then here is my distribution of sample averages as bars, right? Or sampling distribution. The mean is going to be exactly the same, right? Mu for X bars is going to be 32.2. Not different from the population. Standard deviation is smaller, therefore the distribution looks more concentrated around this mean, correct? So therefore it's going to look like that, pretty much. Well, yeah, that's more artistic. And again, we're looking for the probability that in Christian's purchase, what's the probability that the average for the 4-pack is going to exceed 32.0. So here's the distribution of all possible S bars, right? Of all possible averages for the samples of 4. Okay? So here is my 32. And therefore, everything on the right, again, from 32, is going to be the probability what I'm looking for. Now, before we actually go back to jump and calculate that probability, can you tell me, is it going to be a higher probability or lower than before? 0.7475. Higher? Yep, probably higher, right? It's easy actually to see why, because the left tail of the distribution is pretty big for my original population, right? This tail is smaller, right? So therefore, whatever happens on the right side is getting larger, right? So this probability is going to be greater than 0.7475, okay? Well, let's find out what it is numerically. So let's go back to jump, and here it is. So the only thing that I need to change really is the standard deviation, right? Mean is the same. I'm still looking for the right tail from 32, but the standard deviation is half of what it used to be, 0.15. And my probability that I'm looking for is 0.9088. Okay?
So why, on the probability options, why don't they have one that says x is less than q, just without the equal sign?
Without the equal sign. Remember we discussed it yesterday. It would make a difference, right? Because it's only one number.
Oh, that's right.
Yeah.
Got it.
So include or exclude just one number because it's a continuous variable. It's not going to make a splash, right? All right, so 0.9088. That's what it is, 0.9088. So if Christian buys a 4-pack, and his likelihood to get more what he has bargained for is only getting larger, right? In 4-pack, the likelihood that bottles on average are refilled is higher. The next one actually is a little tricky, and I'm going to show you a dirty trick how to do that. Okay, this one. If a customer buys a carton of 4 bottles, what is the likelihood that the total amount in 4 bottles will exceed 128 ounces? So everything that we did so far was about averages, right? What's the likelihood that average can weight is less than 5.97, average of 4 bottles is more than 32.2 or 32.0. It's all about averages, right? This question is about total, okay? So here is the dirty trick that I show every time when I teach that course, okay? I can convert this problem easily. So here is the deal. Christian buys 4 bottles, right? And in every bottle he has certain amount of liquid, right? So X1, X2, X3, and X4, okay? Total is what? Total is sum of these things, correct? And what this problem is asking is what's the probability that this total is going to exceed 128.0 ounces, right? That's what the problem is asking for. Here's what I'm going to do. True or false? If I have inequality, I can divide right side and left side of inequality by the same number, and it's going to be still valid inequality. What do you think I want to divide the left side by? 28? 128? Or something else?
Only the third is 30 then, right?
Yeah, I'm going to figure it out in terms of, so this is the problem about total. I want to convert it into the problem about the average. So if that's the case, sum of the 4 numbers I have to divide by 4, right? So I divide left side by 4 and the right side by 4, right? And it's still valid inequality, okay? So what do I have right here? That's my X bar, agree? That is my average for the sample of 4 bottles, right? Yeah, the dirty trick is to convert total into the averages, right? And it becomes greater than 128 divided by 4 is 32, right? So essentially, it's the same exact problem as we just addressed, right? What's the likelihood that the average is greater than 32? We found that already. I believe it's like 0.9088, okay? So that's one way how you can easily convert the problem about totals into the problem about averages, okay? So let me show you hard and inhumane way to do the same exact problem, all right? In statistics, there is such thing as convolution of distributions. What does that mean, convolution of distributions? Let me illustrate that, okay? If I buy 2 bottles, they come from the same population of bottles, right? They're just part of the same production line, pretty much. Which means that For example, let's say this is my bottle 1. I don't know if I buy a bottle brand new, fresh, right? Close my eyes, pick a bottle from the shelves, you got it. How much stuff inside you don't know because it's a random variable, but we know that it comes from the normal distribution, right? So, and this normal distribution looks like that. According to the foreman, the average for this normal distribution is 32.2, and the standard deviation is 0.3, right? That's the population of all bottles that we ever can manufacture. Okay, if I buy bottle number 2, using the same blind rule, it follows pretty much same distribution, right? I don't know how much am I getting inside this bottle, but it's one number from the same normal distribution, really, right? So, same normal distribution. Well, it looks different because I'm not a good painter, or I can't draw. All right, but it's the same, 32.2, whoops, 32.2, and sigma is 0.3. Now, if I add what's inside bottle number 1 and what's inside bottle number 2, that is also a random variable, right? Because both of them are random variables. So here, and therefore it has its own distribution, its own mean and its own standard deviation, right? That is called convolution of distributions. If you add two distributions together, you're getting a new distribution, which is a convolution of distribution 1 and distribution 2. So the first one is normal, right? With 32.2 and 0.3 standard deviation. The second one comes from normal with 32.2 and 0.3 as the standard deviation. Here is the golden rule, ladies and gentlemen, okay, of statistics. If you have two normal distributions, x1 is normally distributed with some mean and some standard deviation or variance, and x2 is also another variable which is normally distributed with some other mean or the same, doesn't matter, and some other standard deviations, then if you add two variables together and they're normal, then the result, x1 plus x2, is going to be distributed also normally. But here is the trick. The averages add together, but standard deviations not quite. Okay, so you have to add variances and take the square root from that. That's how you convolute two normal distributions. Sum of two normal distributions is also a normal distribution. The averages add together and variances also add together. Not standard deviations, but the variances. Okay? So your standard deviation is square. This is called, I believe, geometrical average, right? Not arithmetic, but geometric average. Or, yeah. So, sigma 1 squared, variance number 1, plus sigma 2 squared, variance number 2, take the square root from that. Okay? All right, so let's go back to our example. This one. So, first bottle comes from the normal distribution, and second bottle comes from the normal distribution. So their sum is supposed to come from the normal distribution, because normal plus normal gives you a normal distribution, right? What about the mean? Means are going to be adding together, right, according to our rule. So it's mu1 plus mu2. So I'm going to say 32.2 plus 32.2. That's going to be the mean for the sum of two bottles, right? Standard deviation is going to be not that pretty. It's going to be the square root from first standard deviation squared plus the second standard deviation squared, right? So that's how two bottles combined together are going to be distributed. So now what I do is I say, well, let's take a look at bottle number 3. All right? Bottle number 3, also just like bottles 1 and 2, it comes from normally distributed population, right? It's normally distributed with 32.2 mean and 0.3 standard deviation, right? So if now to the sum of bottles 1 and 2, I add bottle number 3, x1 plus x2 plus x3, plus x3, what I'm doing is I'm adding one normal distribution and another normal distribution. And we know that convolution of two normal distributions is normal distribution, right? So it's going to be a normal with the mean of now 32.2 plus 32.2 comes from first two, right? And additional 32.2 comes from thing number 3. So I take 32.2, multiply that by 3, right? What about the standard deviation? It's going to be square root from this thing squared plus this thing squared, right? So you have 0.3 squared plus 0.3 squared comes from bottle 1 and bottle 2, plus another 0.3 squared that comes from bottle number 3. Do you see the pattern going on? So therefore, if I'm looking at the total of 4 bottles, x1 plus x2 plus x3 plus x4, it's going to be normal. What kind of mean I'm going to have? 32.2 times 4, right? And the standard deviation is going to be square root from 0.3 squared taken how many times? 4 times, right? Times 4. So that's how the distribution of total of all 4 bottles is going to look like, right? Like I said, it's not a pretty way, but it's going, theoretically, we should get the same exact answer, right? It's just another way to approach exact same problem, nothing more. All right, so now let's take a look. I'm going to create a new page. So x1 plus x2 plus x3 plus x4 is going to be normally distributed with the mean of 32.2 times 4, right? And that gives me 128.8, correct? And the standard deviation is going to be square root from 0.3 squared taken 4 times, which is the same thing as 0.3 times 2, correct? Square root of 0.3 squared is 0.3, square root from 4 is 2. So there you go, and that is 0.6, right? So coming back to my original problem, right? Let's take a look at what this problem was. The problem asked me, what's the likelihood that Christian, when he buys 4 cartons, his total will exceed 128? We know the answer, right? It's 0.90 something something, right? Yeah, yeah. That should be exactly the same thing, right? Because it's just a different way to answer the same question. So here is my distribution of total, right? So x1 plus x2 plus x3 plus x4 distributed normally, right, around the mean of 128.8. That's the mean. And here is my standard deviation represented in some form. And sigma is 0.6, right? And we're asking what's the probability that you buy 4 bottles and the total exceeds 128. So that means it's to the right from the number 128. So this is what happens graphically in my case, right? That's what I should do. And it should give me 0.9083, was that? 88? Okay. So I know the answer. It's just a matter of verifying it with jump now, right? So we will see if I was lying to you or maybe I was telling the truth. All right, let's go back to jump, right? And in jump, I'm going to do some change of my settings, right? First of all, the mean now for the 4 bottles is not 32.2, it's 128.8. And the standard deviation for that monster is 0.6, we know, right? And we're looking for the probability x greater than 128, correct? There you go. 0.9088. Thank God it's the same number. So I was not lying apparently. Okay? Make sense?
Yeah, so the convoluted way gives you the same answer.
Yeah. Convoluted way. So you can convert the problem about totals into the problem about averages, or you can just take it by the face value and say, yep, let's find the distribution of totals. And just attack the problem, you know, in the head-on collision, so to speak, right? Straight how it was formulated. Okay, I believe we're out of time for today, so there is no homework today because we had a brutal exam. Okay, but tomorrow is Friday, right? So tomorrow we're going to take a look at the new material, and I'm going to assign big homework for the weekend. Okay. All right, so we're done for today, and I'll see you tomorrow.